Good morning, fellow mathematicians. Welcome back to another video. That was a close one. I don't want to get flashbacks, alright? You know what I'm talking about. Look at the main channel if you don't know what I'm talking about. We are going to extend ranges of numbers yet again from the naturals to the positive and negative integers. Z, okay? This is what we are going to talk about today, the Z called Z. It's just natural numbers, including all the negatives, and with extending those numbers there are a lot of things that we need to take care of now. A lot of new rules and a lot of cool other extensions, alright? Because something that didn't work before does now work magnificently on the whole of the positive and negative integers. We are going to dive right in. Let us go ahead and talk about the operations. What about addition? I mean, 1 plus 2 is 3, it's still in Z, okay? Does work out. What about 2 minus 3? It's negative 1. Oh, cool. This is also in here. I'm talking about the addition, alright? But maybe you have heard that I said 2 minus 3. Well, Papa Flammy, Flammable Maths. Do people call me Papa here? I do suppose so. They still do, at least for now. You did subtraction, right? You didn't do adding. You're wrong on this one. I mean, you're right on this one, but you're also wrong on this one. I did do addition. What I did exactly is apply the inverse operation here. Inverse operation is just the operation that you can apply to a regular operation, for example addition, to kind of get rid of it. I mean, if you take 3 apples and then I'm going to take them away from you, you're going to have 0 apples. That's what you call the identity with respect to the addition. That has to do with abstract algebra. It's a bit complicated, maybe a tiny little bit. With numbers it's okay, with letters it's a bit harder, alright? But other than that, I was talking about the inverse operation to regular operation, okay? Maybe you can think of another inverse operation that would come to mind. So for the multiplication, maybe that's the division. It's the inverse operation of the multiplication. It's there to get rid of the multiplication, basically, to get rid of all the things after doing the multiplication. Now addition works, multiplication works. I mean, 2 times 1 is 2, it's still in here. 2 times negative 2 is negative 4, maybe you know that. Negative times positive is negative. We're going to talk about this later. It's going to be negative, it's somewhere here. Does work out, negative 4 is in there. So multiplication and addition are still defined everywhere in the positive and negative integers. I mean, that's cool, and nothing about that will really change up until the real numbers. I mean, extending those ranges of numbers also had an extension of operations come with it. So that's an important thing you might want to take with you. Now for the subtraction, okay? Like I said before, subtraction, marked with a little negative sign, is defined everywhere. I mean, if you take 6 minus 8, it's going to be negative 2, and that's cool and all. It's in here, and it does work for each and every number that we can compute in here with each and every other number under subtraction, which is nothing but addition basically, just the inverse operation. So this does work out. That is cool. By extending our numbers to the negative range, we have also extended the amount of operations we can use in here that are valid for all numbers, okay? Before we couldn't subtract numbers all the way along in the naturals because 3 minus 4 gave negative 1. It's not in the natural numbers, didn't work out. But now it does work out by adding the negative numbers. And maybe you can guess already, if we are about to extend those positive and negative integers to the rationals, we are going to get the inverse operation of multiplication, the division. We are going to get it for completely free, just by adding a few new numbers to all of this. This is a big theory in abstract algebra. This is called ring and field theory, and it's a really big part of mathematics, and it's a really hard part of mathematics. But if you are interested in the more theoretical stuff behind all of this and extending ranges of numbers, then check out abstract algebra. It might be the thing for you. So subtraction works to its fullest now. What about division, for example? Division, does that work out? I mean, here we do not need to use the cancellation rule anymore with respect to the addition, because now it does work out. We can subtract stuff from both sides And it does work out, okay? Doesn't really change the set we are in, okay? Works out for all numbers. But what about division? I mean, what about 5 over 3 yet again? Just a simple counter example. It's a bit less than 2. It's a bit more than 1. So it's kind of here somewhere. Doesn't work out, okay? Division does still not work out. But what works out is if we can just cancel everything nicely such that we can get a 1 down here. It's the cancellation rule. Yet again, for example, negative 6 times 2 is, okay, negative 6 is negative 3 times 2 times 2. Okay, now we have this 2 cancelling out. Negative 3 times 2 is still negative 6. Works out nicely. Works out pretty nicely. Alright, cancellation rule still works, but we still can't divide by everything here in the positive and negative integers. This is why we need the rational numbers, why we need to extend even more. Those were the operations. What about all the rules that we have discussed before? Associativity, commutativity, distributivity. They all still work in here. They all work up until the real numbers. So nothing really to talk about, just a few special cases that we are going to discuss today. Other than that, yeah, it just is what it is. They work up until the real numbers. And in most cases, if you extend those ranges of numbers, you are just going to keep them preserved up until you reach stuff like quaternions, octonions, septonions, etc. Stuff is going to get worse from there. If you don't know what I'm talking about, activate the auto-generated subtitles and maybe it's going to spit out what I just said. Other than that, just try to Google it and then you can see that associativity is, for example, missing once reaching the quaternions. I think it's the associativity. Never mind. It's really not what we need to talk about here. It's kind of complicated, mate. So, all those rules still work in the positive and negative integers. But here's some stuff that I would like to focus a bit more on. Namely, applying distributivity, commutativity, associativity to those numbers. Because there's a hidden meaning behind, for example, negative 2. We can rewrite this boy here into something completely different, okay, into the multiplication of things. Basically, it's just hidden in this notation. That's not black math magic that I'm going to do here. It's just hidden in there, okay? Because this is easier to write than what we are going to write now. Negative 2, we are going to write it as the multiplication of things. Namely, each and every negative number is composed of negative 1 and just its positive counterpart. Namely, this is negative 1 times 2. This is all there really is to negative numbers. Those are the negative numbers, all of them. And I mean, if you can handle this, if you know what this right here is and one more rule, then well, you're already done with the positive and negative integers. You can handle all of them. They are so easy to handle once you understand this and one more rule. At first, I would like to show you guys why negative times positive is indeed negative, and it just has to do with this and associativity, I believe. So we are going to dive right in. Let's say we have negative 2 times 3. Okay, teacher said if you triple your debt, then you are going to have negative 6 euros. Okay, yeah, I mean, does make sense, at least tight a little bit. But why is it that way? Why do you get even more negative stuff if you multiply some number by a negative number, at least a positive number, by a negative number? Well, let us write things out, okay? Negative 2 is nothing but negative 1 times 2. Negative 1 times 2. Times 3. Don't forget your times 3. Now, 2 times 3, okay, so here we have used the associativity. This is basically just making use of the associativity that what we have done here, all right? So just as a little side note, 2 times 3 is 6, so this makes negative 1 times 6. Well, a negative 1 times 6 by this convention is nothing but negative 6, and then we are done. Did work out, okay? Pretty nicely. And there's one more rule that I'm not going to prove now. I'm going to prove it at the end of this whole range of number sets of numbers series, okay? Why exactly is negative times negative positive? We are just going to take it as a convention for now, and later we are going to actually show it with numbers and without numbers, alright? Or numbers hidden in letters, basically. So negative times negative is going to be positive plus 1. I'm going to indicate it like this. Meaning overall, we can make use of this rule right here and all the other rules, associativity, commutativity, to actually derive like an algorithm basically for all numbers. For example, -6 times -2. Okay, by what your teacher said, okay, if you could just go by the things that your teacher says, it's going to be +12. But why is it that way? We are going to make use of this rule and this rule, basically. So 6 and -6 is nothing but -1 times 6. I'm terribly sorry. Now times -2 is -1 times 2. Now we are going to make use of the commutativity. So many rules to remember. We are going to just interchange those two. It does work out, all right, giving us -1 times -1 times 6 times 2. Now -1 times -1 per this rule is going to give us, well, +1. Meaning this is +1, no. This is equal to +1, okay, it's just a 1. 6 times 2 is 12. 1 times something is just a something in itself, makes 12. -6 times -2 is going to give us 12. And then we are done. This basically already concludes the most important rules in here. So if you know about this, you basically can also deal with commutativity under addition, blah blah blah. And this is what we are going to talk about next. Commutativity between positive and negative numbers, basically, under addition, is something that many teachers explain wrong. Teacher says, most of the time, at least that's what I still remember from my school experiences, if we have 3 times 2. My teachers back then said, well, you can't use the commutativity rule because, well, that would mean that you would get 2 minus 3, and that's kind of, yeah, it's a bit of a contradiction, right? This is 1, this is -1, ain't working. Yeah, you're right on this, but just because you made use of the completely wrong rules. And here is just where this rule comes in yet again. Negative times positive gives us negative. We can rewrite -2 as +1 times -2. Gives us -2 yet again. Nothing does change. And this is hidden behind notation basically yet again. This is 3 plus -2. And now it makes way more sense, right? I mean, we know that under addition commutativity holds, meaning we can rewrite this as -2 plus 3, just interchanging those two parts. And here, using the associativity, getting rid of all those parentheses gives us -2 plus 3. Well, taking 2 apples away from your 3 gives us 1 apple. Does work out. Works out just like the left-hand side. That's the cool thing. I mean, it does work out nicely, and it's just a bit of calculation, okay, really. And if you can handle this, you can handle way more math problems, because this is one thing that many students really struggle with, just understanding the basic rules. This is why I'm making this little series here on the basic rules. Other than that, we also have like the distributivity law, and this is where many students have immense problems with just simple distributivity. For example, -3 plus 2. -3 plus 2. I have seen terrible things over time, so terrible things. I don't know what they do all the time, but some students just completely ignore the negative sign, make a plus out of that, or they just drag the negative sign to the 3 to get overall -1. Really doesn't make any sense. All you really need to understand is that 3 plus 2 is just another number, and we are using associativity here. 3 plus 2 is 5, and this is just parentheses 5, so -5. And what is -5 exactly? -5 is parentheses -1, parentheses closed, times 5. Meaning overall, let us rewrite this, and let's derive how we can get to a final expression. This is nothing but -1 times 3 plus 2. And after this small step, everything is just so much more apparent than before. Now we can make use of the distributivity. That's the multiplication of things, and here we have addition in here. -1 times 3 plus -1 times 2. Let us write everything out. This is -1 times 3 plus -1 times 2. -1 times 3 is nothing but -3. And then plus -2. Plus -2 is per, let me see, where did we have the rule? Yes, we had it up here. It's just plus -2 is just -2 overall. I'm terribly sorry. -3 minus 2 is -5. And it does work out, just what I said before. You can also calculate stuff here together and then track the negative sign on there and it works. But as soon as there do appear letters, for example, beta, gamma, delta, sigma balls, then everything just collapses for most students because there ain't numbers anymore. It's not easy anymore for whatever freaking reason, alright? But if you just know about those simple rules, everything about negative numbers is basically at the palm of your hands, okay? Just at the palm of your hands. Other than that, we have talked about multiplication here. Also, if the division is satisfied here, so like cancelling out everything to 1 down here in the denominator, then we can also deal with division, basically. For example, -6 over -2. I mean, 6 over 2 is going to cancel out completely to a 3. And negative over negative. I said before that division is basically just multiplication, just how subtraction is just addition. And there's one simple rule that we need to follow here, namely that 1 over -1 is nothing but -1 over 1. Okay, we're going to go into more detail why this right here is what it is in the rational numbers, nothing but -1. Meaning overall, what we have here is -6 over 2 times -1. So we have 1 over -1 is -1. We are going to track it to here. You can bring this -1 to the front. You can use the commutativity, negative and negative becomes positive, to land at exactly 6 over 2, which is 3. And then it works out. Just a little side note on division in the positive and negative integers. Last two things. The ordering in the positive and negative integers, and also what the 0 is all about here. 0 is just like before. It either destroys everything if you multiply it by it, or it's just indifferent if you add to it. Okay, 3 plus 0 is just 3. Okay, nothing did change. Coolio, we still can divide by it, blah blah blah. 0 is pretty boring, except for the cases when it causes immense troubles for us. Now for the order relation, so greater, less, greater or equal, less or equal to something in the positive and negative integers. Now, I hope you agree with me that if you have $5, then you have more dollars than if you wouldn't have any dollars at all. For example, a debt of $3. So 5 is greater than -3. Okay. So I hope you agree with me that this is indeed true. If you have $5, then you have more dollars than if you would have $3 in debt. Now, what would happen if we were to multiply both sides by -1? Okay, that's the whole point of this order relation stuff here. Order relations work just like before. Okay, you can basically count stuff and then you can put a little ordering in here. Now, if we want to multiply both sides by -1, what is going to happen? We are just going to calculate it and we are going to leave our order relation out of the way for now. That means multiplying both sides by it gives us -1 times 5, and then something, we don't know what it is, -3 times -1. Negative times negative is positive. Okay, so on this side we are going to have 3. And on this side, negative times positive is nothing but positive. Meaning overall, this is negative times positive is nothing but negative and terribly sorry, leaving us with -5. And now if you have $3, then you do have more money than if you would just have $5 in debt. Meaning 3 is greater or equal to -5. Meaning what to do? Once you multiply both sides by -1 on an order relation, you're going to flip it. Okay, this is just a rule of thumb here, and if you can't remember this for shit, then well, you can just go by this little calculation and then you're already done. Okay, just imagine it with numbers and then you are basically good in all the regular sets of numbers. And this concludes my little talk about the positive and negative integers. I hope you did enjoy this video. If you did, please like, subscribe, make a comment, channel if you like. Don't forget to buy those new algebra merch. It looks pretty good. And also check out the main channel, subscribe to it. If you did enjoy the video, then please watch it to your fullest. Watch it several times to increase the watch time here for the YouTube algorithm. And other than that, leave some feedback down below. And I'm going to see you in the next video. Ciao. Have a flamable day.